Hello everyone. This video covers section 4.4, Gaussian quadratures. Now, before we go to this section, so far, when it comes to integration, which it has been sections 4.3 to 4.6, okay? Mainly, this is based on the Newton codes, and part of this was the trapezoid and the Simpson's rule, or the original trapezoid and the original Simpson. Now, this one needed equally spaced points. That makes it easier for computations, but this may reduce the precision. So it may reduce the precision, but it's good for computational purposes, and it's also easy to create the composite trapezoid, the composite Simpson. But let's see why the equally spaced points may not be the best thing. You want to have a specific precision. For example, here on the first table, we have three cases here using the original trapezoid method, which you evaluate the function at these endpoints and technically just find this area. So you can see that this one underestimates the area, so there's a big gap here. This one overestimates the area by this extra stuff, and here there is also a big gap. Okay, so now the idea of the Gaussian quadratures is that we're going to not rely on equally spaced points anymore, like we did with the Newton codes, and the point is to increase the precision. So remember, we want to be precise, where precision was defined, I think, in section 4.3. Okay, so precision, I think it was defined in section 4.3. So you should look that again, because we're going to look over precision multiple times. So the Gaussian quadratures will have the following form. Okay. So technically, if you expand this will be C1 times f of x1, C2 f of x2, all the way to Cn f of xn. Okay. Now the goal is going to be to find the constants, the n constants C1, C2, all the way to Cn, and also the x values, x1, x2, all the way to xn, to minimize the expected error. And by that I mean, you can see now, if we don't rely on equally spaced knots anymore, or points, you can see that this approximation is better than this one. So here, what we have is the following. At each node, you're technically going to have to find two things, x1 and c1. So these are two different variables. So you have to do this all the way to xn, where clearly all of the x's belong to a and b, are between a and b. And then c1 to cn will be the constants. So technically here we have two n parameters. Okay. And we want to, like I just mentioned this already, you want to choose this. So you want to choose them, or they will be chosen to minimize the expected error. And here by expected error, we're talking about we're trying to be as precise as possible. So therefore, what we're going to do, we're going to choose a class of polynomials. So we're going to have a polynomial class of degree 2n minus 1. And this one has 2n parameters, which is what we need. And this will be the largest class of polynomials for which is reasonable to expect to have or to expect a formula to be exact. And remember, exact, this is where I talk about the precision. Okay? So you need to remember what the definition of exact means. Now, for example, let's say that n is equals to 2. So if n is 2, then you're going to have 2 times 2 minus 1, which is equals to 3, if we plug it into this formula. So we're going to rely on the third degree polynomials, or more precisely, you want it to be exact up to third degree polynomials. Now for the Gaussian quadratures to work, you're going to have to actually integrate from minus 1 to 1. So a will be minus 1 and b will be 1. We need that so we can use the properties of integral, where you find even and odd integrals. That makes calculating their areas a lot easier. Okay, so this is what we want. Need to figure out C1, f of x1, C2, and f of x2. And we want it to be precise up to the third degree. So therefore, we need C1, C2, x1, and x2. Now, if we go with the definition of exact, which is technically you had to do this in the test. For x to the 0, which is equals to 1, we have the following: the integral from minus 1 to 1 of the x. This implies the c1 times 1 plus c2 times 1 should equals to 2. Now, if we pick x, then the integral from minus 1 to 1 of x dx implies that c1 x1 plus c2 x2 will be equals to 0. Why? Because remember, the integral from minus 1 to 1 of x dx is equals to 0, so it should be obvious, but you should check it if you want to convince yourselves. Then if we do x squared, the integral from minus 1 to 1 of x squared dx, you should check that this gives you actually 2/3. So that means c1 x1 squared plus c2 x2 squared is equals to 2/3. Then finally, you do it for x cubed. And this is the reason why we're going from minus 1 to 1. You do it for x cubed. That means that c1 x1 cubed plus c2 x2 cubed, that is equals to 0. Now, this is a little more tricky than the question you have on the test, because on the test, these values were given. So all you had to do was figure out C1 and C2. Luckily, there will be an easy way to figure out those values. In fact, they will just be given to you. So in this case, you can check that C1 has to be 1, C2 has to be 1, x1 equals to minus radical 3 over 3, and x2 equals to radical 3 over 3. So we will see in the next page how we get these values. This will give you precision 3, which is what we want if we use these values. Now, to solve the system of equations from the previous page by trial and error, it can be a little bit tricky. So instead, we're gonna use the help of some new polynomials called the Degenerate Polynomials, which it has the following two properties. The first one is the following, that for each n, the polynomial is a monic polynomial of degree 1. Remember that monic just means that the leading coefficient is 1, like x cubed plus 2x squared plus x plus 1 is a monic polynomial. X to the 4 plus 100x minus 1 is also a monic polynomial, but 6x squared plus x is not a monic polynomial. Okay? And second, it has the property that whenever you integrate p of x times the monic polynomial, as long as px is a polynomial of degree less than n, that this will be equals to 0. Okay. Now here is a list of the first four legendary polynomials. So p0 is 1, p1 is x, p2 is x squared minus 1 over 3, and so forth. Now these polynomials are going to give you the x values, and then you're going to use the x values in the next term to find out the coefficients or the z values. For example, for this one, you can see the x squared minus 1 over 3, if you say this equals to 0, the x squared will be 1 over 3, or the x is equals to plus or minus radical 3 over 3, which you recall from the previous page, these were the values for x1 and x2. Remember, x1 radical 3 over 3, and x2 is minus radical 3 over 3. In the same way, you can use p3 to find the values for x1, x2, and x3 if you have a third degree polynomial. Remember your factors, so it will be x squared minus 3/5, and then just find the values for x1, x2, and 3, which clearly the first one is 0. By the way, this in decimal form is equals to plus or minus, I believe, 0.5773502692. So therefore, we're going to use the Legendre polynomials to find the values for x1, x2, and once you have it, we're going to use theorem 4.7, which says the following. Suppose that x1 all the way to xn are the roots of the n Legendre polynomial, and therefore for each I from 1 to n, the number ci is going to be defined this way. So if Pn is any polynomial of degree less than 2n, then the integral of this is going to be equals to this. This one is missing one subscript, so here is from j equals to 1 to j is not equals to I. For example, for our case, let's say that you wanted to find c1. So c1 should be the integral from minus 1 to 1 of the product from j equals to 1, j is not equals to I, all the way to 2, because remember here the value for n is 2, of x minus x2 divided by x1 minus x2 dx. Once you simplify this part, and you should check this is equals to the integral from minus 1 to 1 of x minus 1 over radical 3, because that's what we found radical x2 to be, and then on the bottom it will be minus 2 over radical 3. Okay. Now you can break this into two integrals. It will be minus 3 over 2, the integral from minus 1 to 1 of x dx plus 1/2 the integral from -1 to 1 dx. And once you simplify everything, this is equals to 1. So that's how we get C1. So similarly, so you do the same thing for C2, we will get that C2 is equals to 1. And luckily for you, as you can see, you already have a table that has done the computations for you, and you should be able to use this when you do the homework or the exams. So this is the one we did right now. So for n equals to 2, this is the square root of 3 over 3 minus the square root of 3 over 3. So these are the x values. So x1 all the way to xn, and this is c1 all the way to cn. So you can see for this one is 1 and 1, which is what we just found right now. Now if n was equals to 3, I already mentioned in here that clearly one of the x values has to be 0 for this one, and the other ones will be the square root of 3 over 5. And if you look to the table, you can see the 0 here, and this is the square root of 3 over 5 minus the square root of 3 over 5. And then you do the integrals. This is the value for C1, C2, and C3. But again, they are given to you, so you can just use them from now on. You still should be able to find it, at least after C3, though. That could be a good question for the exam. Alright, so let's do an example now and see how this works. Alright, so let's say that you want to approximate this integral from -1 to 1. And here the question has to give you the following. So it has to tell you that it wants n equals to 2. That's why we only have C1 and C2. And we already found this value, so you can just refer to the table from the previous page. Remember, C1 and C2 were equals to 1, and x1 was equals to minus radical 3 over 3, and x2 was radical 3 over 3. Okay? Now, just for comparison purposes, to find the exact solution using integration by parts is not that hard, so you should check this by yourselves. But the exact solution to this is, well, exact is 0.87888463. Well, exact up to this many places. Therefore, if we use the Gaussian quadrature, all we have to do is use these values in here. So this will be equals to C1, which is 1, and then this should be f of minus radical 3 over 3 plus C2, which is again 1, and then f of radical 3 over 3, which will give you minus radical 3 over 2 square e to the radical 3 over 3 plus 1 times radical 3 over 3 square times e to the minus radical 3 over 3. And I believe this is 78089869, which you can see is not as close, but this was just n equals to 2, and it was very simplistic to get this answer. You should check that if you use n equals to 3, which you already have the value from the table, it will give you a more precise calculation. So for n equals to 3, then you will have to find C1 f of x1, C2 f of x2, and then C3 f of x3. So just give it a try. So just try this one, and you'll see it's closer to the exact solution than this one. And you already have these values on the table. All you have to do is plug it in. Now, even though this is very simplistic to apply, there is a big drawback, and the drawback is that it only works for integrals from -1 to 1. Now most of the integrals are usually not from -1 to 1. Luckily, you can just do a change of variable and change everything into 1 to 1, and that's what the next part will do. So this will be the Gaussian quadrature for an arbitrary interval. So this is the formula you're gonna use to change it. So t is gonna be 2x minus a minus b divided by b minus a, and therefore x is gonna be equals to 1/2 b minus a t plus b plus a. Okay, so now here a and b could be anything. So for example, let's say you are trying to integrate 0 to 1 of x squared e to the minus x dx, which is the interval we did. We're just changing the limits. So here the value for a is 0, and the value for b is 1. So therefore x is going to be t times 1 minus 0 plus 0 plus 1, everything divided by 2. Which means from here that x is going to be equals to t plus 1 over 2. So therefore we do a substitution. This is going to be the same thing as 1/2 the interval now from -1 to 1, which is what we want, and this will be t plus 1 over 2 square e to the minus t plus 1 over 2 dt. And then we just use the same formula. So this will be 1/2 times 1, and then it will be f of minus 0.577350 and so forth, plus 1, which is this one right here, everything divided by 2, plus 1/2 times 1 times f, and that will be 0.57735, keep it going, plus 1, divide everything by 2, and this I believe is 1/2 times 0.03615130. So please just check these computations. This is 0.286695569, and this is around 0.1594 104309. Now in this case the exact solution is 2 minus 5 over e, which is 0.1606027 so 4. So now let's compare that with the previous methods. So if you do the trapezoid will give you 0.1839 397206, and Simpson will give you 0.16 at 24 016835. So you can see just the way it was intended. This is more precise than this two. Simpson's rule is actually pretty close, but the Gaussian quadrature is still better than this one, and it's definitely much better than the trapezoid. Alright, so that's it for section 4.7.